Good evening, everyone. My name is Dyani Peterson, and I am presenting my capstone project for this capstone class entitled Machine Learning for Predicting Autism Spectrum Disorder, Utilizing Clinical Data to Enhance Early Diagnosis. This research was completed under the guidance of Dr. Lubina Pinky with the support of AIMAHEAD and MedStar Health. I want to start with the core motivation that children with autism spectrum disorder are being identified too late, which eventually in the data to that changes that already existed in their medical records. This project is about using data more intelligently. So let me set the stage for this problem that this study addresses. Autism spectrum disorder affects 1 in 36 children in the United States, a number that has risen sharply over the past 2 decades. The critical issue is not just prevalence, but timing. Current research shows that intervention before age 3 produces substantially better long term outcomes in language, cognition, and adaptive behavior. Yet, the average age of a formal diagnosis remains between 4 to 5 years old. Most children miss that window entirely. So, why the delay? Current diagnostic tools like the ADOS, which stands for the Autism Diagnosis Observation Schedule, and the ADIR, which stands for the Autism Diagnostic Interview Revised, are behavior assessments that requiring a trained specialist. They cannot be administered until symptoms are obvious, and they are research intensive, and access to specialists is deeply unequal. During my literature review, I found out that Black and Hispanic children are diagnosed later and at lower rates than white peers, not just because ASD is less common in those populations, but because the system fails them more consistently. During this opportunity, I want to highlight that prenatal and contextual data, birth weight, gestational age, APGAR scores, and the neighborhood deprivation is already in electronic healthcare records from the moment a child is born. We are not using it. Machine learning gives us a systematic way to start, and it also offers earlier and scalable equity aware risk stratification while using the EHR data. So before I present my hypotheses, let me briefly orient you to the study design. First, I have compared three machine learning models head to head using 29,331 pediatric patient records from the Aiding Ahead Data Bridge MedStar Health. This data set was split 70-30. 70% I used for the training data and 30% I used for the testing. And all performance metrics were evaluated using the 1,000 bootstrap resamples to generate 95% confidence intervals, which is very essential for the statistical comparisons that I will walk through later on in this presentation. So the central research question that I had developed was that can machine learning models be trained on prenatal, clinical, and social economic EHR data accurately predict ASD risk? And do such models perform consistently across demographic subgroups? So within this study, I have formulated two hypotheses. The null hypothesis states that there is no statistically significant difference in the AUC, which is area under curve, between the lasso regression model and the neural network model. The alternative state hypothesis states that the neural network will outperform both linear in tree-based models by detecting nonlinear patterns and interaction effects. One distinction that is worth recognizing here is that interactions in nonlinearity are not the same thing. Interactions are when two variables come together, have a larger combined effect than either has individually. And nonlinearity is when the relationship between a single variable and the outcome follows a curve rather than a straight line. The neural network captures both, but the lasso regression model captures neither, unless you create them explicitly. So now let me walk you through the three models and why each was chosen. So the first model that was chosen is called the lasso logistic regression, which is the statistical standard. It adds an L1 penalty to standard logistic regression, which shrinks non-essential predictors to exactly zero, performing embedded feature selection automatically. It produces odds ratio that clinicians can interpret directly, and it models linear additive relationships between predictors and the outcome. The classification tree is the interpretable baseline. It produces a transparent flowchart of yes and no decisions that anyone can follow. For the classification tree model, I used the RPart engine specifically because it integrates natively into the Tidy Models pipeline, ensuring the same pre-processing and evaluation steps were applied consistently across all three models. Then we have the neural network model, which is a nonlinear model, a single hidden layer of 5 neurons trained for 100 epochs. I do want to be transparent here that I was planning to use the random forest in XGBoost for my original models, but due to the computing environment that I'm using in the MedStar server, I could not compute those type of models. So this is why I went this route. Um, and also I was planning to use the MLR3 framework, but I was trouble with having that as well. But with the neural network, I used the InNet engine, which is selected because of its stability, and it was really more efficient to use. Um, so with the data set I have talked about earlier, the split, which is 70-30, using the stratified random sampling. Stratified means that is preserved the proportion of ASD cases in both the training and test sets. All model training happened exclusively on the 70%. The 30% test set was completely withheld until the final evaluation to prevent any data leakage. Pre-processing was applied uniformly across all three models through Tidy Models process. The missing categorical values were assigned in unknown category rather than being dropped or imputed. In the EHR data, missingness is a rarely random. In this term, a patient with a no document tobacco history may be reflecting reduced prenatal care engagement, which is clinically meaningful in this term. For continuous variables, I have used the median imputation, and all numericals were then z-score normalized. And then for the hyperparameter tuning was done via fivefold cross validation. The lasso penalty, lambda, and the tree depth were both tuned during this hyperparameter process. So for the evaluation, I did more just beyond the AUC, which is the area under curve. I have computed the accuracy, precision, recall, specificity, NPV, the Breyer score, and collaboration plots. all with bootstrap 90%, 95% confidence intervals. The Breyer score measures calibration, not just how well a model ranks patients, but whether its predicted probabilities actually reflect real world ASD rates. This distinction matters enormously for clinical use. So let's walk through my key findings. To start with the recall, which is for the decisions tree, it was 0.963. For the lasso regression, it was 0.967. And for the neural network is 0.964. Every model identifies more than 96% of true ASD cases. That consistency across very different algorithms tells us that the predictive signal in this EHR data is robust and real data that works. Now, the ROC AUC. The neural network leads at 0.861 and the lasso is at 0.849 and the decision tree is 0.768. The decision tree's confidence interval does not overlap with the others. It's known statistically the weakest discriminator. But here's the headline finding. The neural network confidence interval of 0.850 to 0.871 and the lasso confidence interval of 0.838 to 0.860 does not overlap with the others. It is statistically the weakest discriminator. Um, that this overlap does mean that the performance difference is not statistically meaningful. You cannot declare that the neural network is the winner on discrimination alone. So now with the Breyer score, um, the lasso regression model achieves at 0.099 and the decision tree is at 0.106 and the neural network is at 0.139. The neural network's Breyer score is 40% worse than the lasso's. The Breyer score measures the calibration, whether predicted model probabilities are reliable as absolute risk estimates. A model that ranks patients well but assigns unreliable probability is hard to use clinically. You cannot tell a clinician a patient that has a 45% risk of ASD if those probabilities are systematically off. Taking everything together, matching AUC within statistical uncertainty, highest recall, and best collaboration, the lasso logistic regression is the most comprehensively strong model for clinical applications. So let's look at the ROC curves of all three models and the calibration plots. On the left, all three ROC curves are plotted together. The ROC curve plots sensitivity, the true positive rate, on the y-axis against the false positive rate on the x-axis across all possible thresholds. The diagonal dotted line is the random chance. The closer a curve hugs the top left corner, the better. The neural network and lasso curves are nearly on top of each other, which is exactly what the overlapping confidence intervals confirm statistically. The decision tree sits noticeably lower and has a stepwise shape because a tree produces only a small number of discrete probability values rather than a smooth probability distribution. On the right, you can see the calibration comparison. The lasso is the only model below a Breyer score of 0.10. Its calibration plot shows a near diagonal alignment that its predicted probabilities closely track the actual observed ASD rates across all risk deciles. The neural network's calibration diverges from the reference line, particularly at lower risk levels. This is the core reason it needs post hoc recalibration before clinical use. Platt scaling or isotonic regression could bring its probabilities in line, but that step has not yet been applied. So with this slide, I did the top three predictors of the ASD risk by each model. Permutation important works by randomly shuffling one variable at a time, breaking its relationship with the outcome, and measuring how much worse the model performs. The bigger the performance drop, the more important the variable was. So the top three from out of all of the models, age group is the number one predictor in all three models by a substantial margin. This reflects the developmental windows during which ASD risk becomes detectable. Older children in the dataset are more likely to have sufficient clinical contact for a diagnosis. The tobacco history ranks in second in the lasso and in the decision tree. This likely reflects the prenatal care quality and maternal health conditions associated with developmental risk rather than a direct biological mechanism. And sex is the third consistent predictor across all three models in line, which is the well documented to 4-to-1 male to female ratio with ASD. So this is a confusion matrix of the neural network. Of 879 true ASD cases, the 614, which is 69.9%, were correctly flagged as high risk. These are true positives. The 265 missed cases, which is 30.1%, are false negatives. In a screening context, these are the most consequential errors. Each missed case is a child whose diagnosis may be further delayed. Of the 7,922 true non ASD patients, 7,027, which is 88.7%, were correctly cleared. The 895 incorrectly flagged patients, which is 11.3%, are false positive. Roughly in 1 in 10 non ASD patients are receiving an unnecessary high risk flag. Clinicians and health system administrators would need to weigh that false positive burden against the benefit of catching the true positives earlier. So let me bring the key takeaways from this study. First key is that data works. All three models achieved over 96% recall. The predictive signal instructed EHR data is robust and reproducible across very different algorithms. The second key is that lasso logistic regression is the most clinically well-rounded model. It matches the neural network on discrimination within statistical uncertainty, achieves the highest recall at 96.7%, and produces the most reliable probability estimates with a Braille score of 0.099. For any clinical deployment scenario, lasso is the stronger candidate. And the last key takeaway is that collaboration matters e as much as AUC. The neural network's 40% worst Braille score is finding that most ASD machine learning papers will miss entirely. They report the AUC and stop there. Collaboration determines whether you can actually communicate the probability to a clinician or family as having meaning something. And then the last key is that missingness is a clinical signal. The unknown categories were preserved in pre-processing turned out to be independently predictive, which reflects patterns of reduced healthcare engagement that are themselves associated with the data risk. Also, we could see that the age, tobacco history, and sex are the most consistent predictors across all models, which is in line with epidemiological literature. For the clinical implication, that a validated EHR-based screening tool could compress the diagnostic timeline without requiring specialist availability, flagging children for prioritized development surveillance before behavioral symptoms are obvious enough to trigger a referral. So some limitations in the future directions I will go over. One of the limitations is that I only had one data set to work with. Um, these models were trained on a one health system that was not really generalized to different demographics, EHR platforms, or clinical workflows. Um, and the outcome variable, which is the ICD code F84, reflects documentation, not ground truth. The children who have ASD but have not received a formal diagnosis will be misclassified as negatives in the framework. This disproportionately affects underserved populations where diagnostic access is most limited, the very groups this study is designed to help. Also, with the SHAF analysis and formal subgroup for fairness, disaggregations was not completed in this project just due to the server complications. For the further future directions, what I'm looking forward to is the external validation across diverse health systems, so adding more data sets, the subgroup fairness analysis with equalized odds, the neural network recalibration, and data enrichment through birth record lineage and clinical note NLP, and most ambitiously the time to event modeling to not just predict whether a child is at risk, but when that risk is likely to manifest as a formal diagnosis. And I would like to acknowledge several people that has helped me during this project. My advisor, Dr. Lubina Pinky, for her guidance and her expertise and her unwavering support throughout this project. Dr. Jamie Spicer, who's from Wake Forest University. She is my assigned Aim Ahead mentor. I'd like to thank her for her guidance and feedback on this project. Also, would like to thank the Aim Ahead and MedStar Health for providing access to this clinical data set that has made this research possible. And also, I would like to thank Meharry Medical College, the School of Applied and Computational Sciences, for helping me with my training and helping me making this research possible. And thank you to my cohort for theirs and family for support. And that is the end of my presentation. And